Okay, what I'm going to do today is summarize the material that we talked about last time, this transition from the first part of the semester where we were simply checking the inventory, checking what was in the box that we bought back from Sears, the transition from that to inferential statistics, and in particular interval estimation. I think fundamental to estimation is, to understanding it, is that you think in terms of central limit theorem, that you think in terms of sampling distributions of sampling means and then later sampling distributions of sample proportions. The opening remark, I think, about estimation was we distinguish between point estimation, which is essentially useless, and interval estimation, which is extraordinarily powerful. Point estimation, when you're talking about, when you're investigating or trying to estimate mu, is X bar. That is the average of the population. Your best estimate of that average is the sample average if two conditions have been met. If n is large and if the sample has been selected randomly. We talked of going into a community with n equal to 200, that is, n is large, and we assumed that we had selected that group randomly. We measured their IQ, and the average of the group was 105. That being the case, because X bar, under these two conditions of large sample and random selection, is an unbiased estimate of mu, the best single guess of mu, the point estimate of mu, is then 105. The likelihood of that actually obtaining, we agreed, was almost infinitesimal. What you're requiring for that to obtain is that single sample mean, X bar, when you consider the sampling distribution of all sample means, is right at the center of the distribution and so equal to mu. It's clearly much more likely, the probability is much higher, that this particular X bar will be some distance removed from the center of the distribution. So we then talked about interval estimation, and interval estimation takes the form, the estimate of mu equals X bar plus or minus some range of scores that center around X bar. If we look at this sampling distribution of sample means, it has, and we know this from central limit theorem, it has a mean of mu and a standard deviation equal to sigma over the square root of n. We've already acknowledged today that you have an unbiased estimate of mu, and that is X bar. Looking at this formula then, X bar plus or minus some range of scores centered on X bar, you and I are simply going to set up some range of scores. And that range of scores will include either 95 or 99% of all of the area under the curve. Another way of saying that is that it will include 95 or 99% of all scores in the distribution. And trying not to sound like John Travolta in Pulp Fiction, yet another way of saying that is that it will include 95% of all possible sample means drawn from this particular population with sample size set to 200. And we defined that distance because this x-axis can be measured in units called standard deviation, and we know from central limit theorem that the standard deviation of a sampling distribution of sample means is sigma divided by the square root of n. That we have to go some number of standard deviations either above or below the mean. That number can be measured as z. That is, we would simply go to the z table and determine the number of standard deviations that we would need to go in order to isolate either 2.5% and 2.5%, 5%, or 0.5% and 0.5%, 1%. So it's z standard deviations where the standard deviation is sigma over the square root of n. Before I go any further, are there any questions? You're not helping the folks at home. I'm sure the folks at home are going, I got questions. Why don't they ask them? The next idea that we introduced into this discussion was the notion of confidence levels or confidence intervals. And I indicated, and a confidence level is simply the level of confidence associated with the estimate. And by convention there are two, 95% and 99%. And that's reflected here in terms of capturing either 95 or 99%. So, and the confidence level affects the value, in fact it determines the value of z. When the confidence level is 95%, this z-score must be plus and minus 1.96. That is, if you wish to isolate 95% of all of the scores in this distribution, you must go 1.96 standard deviations above the mean and 1.96 standard deviations below the mean. If the confidence level is 99%, then that value of z is plus and minus 2.58. That is, if you wish to isolate 99% of all of the scores, if you wish to be 99% confident in your estimate, you have to go 2.58 standard deviations below the mean and 2.58 standard deviations above the mean. Des questions? Yes.
So you determine the standard deviations for each of the confidence levels. You always have to?
In order to generate a confidence interval, you must know x bar. You must know, in this case, sigma and n. And you must be informed of the confidence level. In a naturally occurring situation, the researcher decides the confidence level. The most common of those two is 95%. When you hear reported on television or in a magazine or in a newspaper, wherever, that the level of support for war against Iraq is 43%, the margin of error is plus and minus 4 percentage points. That estimate typically is generated at a 95% confidence level. So what it says is that the researcher is 95% confident that somewhere between 45% minus 3%, which is 42%, and 45% plus 3%, 48%, of all Americans would support war with Iraq. And we will look at proportional data, I won't say momentarily, but in the context of this chapter. Are there any other questions? No? Let's then look at situation 1. And situation 1 is one in which you're estimating mu. N is large and sigma, the standard deviation of the population, is known. Before we go any further, it's one in which you're estimating mu, the population mean. N, the sample size, is large, and sigma, the standard deviation of the population, is known. Before going into an example, I want to point out to you that this is an unreal situation. If you recall, when you were required to compute standard deviation and variance, the very first thing you did was to compute the mean of all of the scores, yes? And then subtract that mean from each of the individual scores. Well, since we're dealing not with a distribution of individual scores, but in a sampling distribution of sample means, we're dealing with a distribution of sample means, then the first step in computing the variance or standard deviation of that distribution would be to subtract from each of those sample means mu, the mean of the population. This is the thing you're trying to estimate. It's therefore an unreal situation. That is, you're estimating sigma because sigma is unknown. You're estimating mu rather because mu is unknown. But at the same time you know sigma. Whereas we've just decided or observed that in order to compute sigma, you would have to know mu. Yeah. It's simply an unreal situation. I go through this situation, albeit unreal, because I think it leads to an easier understanding of two situations that are not unrealistic. Let's look at an example in the text on page 163. On page 163, a little more than halfway down, it says, as an example, suppose you wanted to estimate the average IQ of a community and had randomly selected a sample of 200 residents with a sample mean IQ of 105. Assume that the population standard deviation for IQ scores is about 15. What we know from this then is that X bar equals 105. We know that N equals 200, and we know that sigma equals 15. Would you agree? Are there any questions at all about any of these values? It's on page 163. You go clear over there? Yeah? This is then just a matter of plug and chug. The formula for estimating mu is X bar plus and minus some z-score multiplied by the standard deviation of the distribution, sigma over the square root of n. Yes. But all you need then is to know the confidence level or confidence interval. And let's assume you were asked to construct a 95% confidence interval. That is, you we're instructed to set the level of confidence at 95%. Would you agree that this is pretty automatic? Your estimate of mu would be x bar, the sample mean, which is 105, plus and minus the z-score, which is a function of the confidence level. And since the confidence level is 95%, we decided that we would have to go out 1.96 standard deviations in either direction, or in both directions from the mean. So the z-score here is 1.96. Sigma is 15, divided by the square root of n, which is 200. Are there any questions as to how we moved from the general formula to this specific application? No? If you perform that computation, at least according to Healy, the answer is 105 plus and minus 2.08. That is, you're 90, based upon these data, and I would emphasize, based upon analysis of only 200 residents in this community, you are now 95% confident that mu, the average score of the community in general, is somewhere between 105 minus 2.08, which is 102.92, and 105 plus 2.08, which is 107.08. Are there any questions about this situation, about anything associated with it? The general formula, the specific application? Somebody who's watching this at home is screaming for somebody to ask a particular question, but they're not going to help. Let me talk in this context about confidence intervals. We talked about confidence interval equaling 95% or confidence interval equaling 99%. In either case, you would agree, there is some likelihood that the estimate is incorrect. There is some likelihood that the average IQ of this community as a whole is either below 102.92 or above 107.08. Would you agree? What is the probability, what proportion of all scores in this distribution are below 102.92? Come on, sports fans.
Is it 2.5%?
It would be 2.5% because we have isolated 95% of all of the scores. We generated a 95% confidence interval. If that's the case, we haven't isolated 5% of the scores, and those are distributed evenly at both tails of the distribution. So 2.5% of them are here, and 2.5% are here. So overall, there is a 5% likelihood that the average IQ of this community as a whole is either below 102.92 or above 107.08. And that is represented as the level of alpha. when you set the confidence interval to 95%, you have established an alpha value of 0.05. And when you set the confidence interval equal to 99%, you've set alpha equal to 0.01. The only difference between these confidence levels and the values of alpha, which alpha indicates the likelihood of being wrong, is that one is expressed as a percentage and the other as a probability. This, you understand, is equivalent to 5%, and this is equivalent to 1%. That is the inverse of these values. As we build on this, let me ask again, are there any questions? Yes.
Maybe I missed this part, but the confidence interval, how did we know that 95% was the one matching the curve to figure out the 2.5% on each side? Because the 2.5 equals 5%, so that's the other 5%. But based on the answer that we got when we estimated mu, how do we know it's the 95% confidence interval?
I'm not sure that I understand your question, so I'll give you a bigger answer. I think I might catch your question in the end. This distribution, first of all, is normal. And so it is symmetrical. It's symmetrical about the mean, mode, and median. Yes. We know that if you go to Appendix A, looking for a value of z, that is a number of standard deviations, that isolate, that has a value beyond z of 2.5%, you'll find that it's 1.96. That is, if you go 1.96 standard deviations below the mean, 2.5% of all scores are even lower than that. If you go 1.96 standard deviations above the mean, you'll find then that 2.5% of all scores are even higher than that. Not only then is this distribution as a whole symmetrical, so too is the range of scores that we've generated. The area under the curve above the mean is precisely equal to the area of the curve below the mean. The only other thing, I apparently haven't answered your question. The only other thing I can think of here is that we were instructed to set the confidence level equal to 95%. The researcher typically decides that herself or himself, but I'm thinking in terms of an exam. And on an exam, you would be instructed to use either a 95% confidence level or a 99% confidence level. And if it was 95%, you would then know that this value of z is plus n minus 1.96. And if it was a 99% confidence level, then you would know that that z value is plus and minus 2.58. Are there any other questions? About anything? Life? The portrait of the artist as a young man? World War II? European Champions League? Cricket World Cup? None. Why all the faculty have the exam on the same day?
Is it better to use like a higher confidence interval, or does it not matter?
That's a good question, because it would appear that there is nothing to lose by adopting higher confidence levels. That is, it would appear routinely to be better to use a 99% confidence level than a 95% confidence level, because the likelihood of being wrong, that is, the likelihood that your estimate of mu would be outside of that range of scores, is then 1% rather than 5%. The trade-off is between that increasing level of confidence and the increasing range of the error component. That is, and the error component is the plus and minus. So in our example, 105 was the point estimate. The plus and minus 2.08 represents the interval, but it represents the error too. And that's how it's reported to you and I on TV, for example, when we're told that the average IQ was 105. The error in that was plus and minus 2.08 IQ points. You understand that if all other things being, well, let me go back further. You understand that what determines that error rate, or that error component, is this section of the computation. So that all other things being equal, if sigma remains unchanged, and if n remains unchanged, what determines the width of this range of scores is the confidence level. If we were to go from 1.96 to 2.58, that is from 95% to 99%, you would agree this score would go up. That is, the range of scores that we're establishing now would be wider. Would you agree? Because we'd be multiplying sigma over the square root of n, not by 1.96, but by 2.58. So the trade-off here is between higher levels of confidence that your estimate will include the parameter, the target parameter, and the width of the confidence interval, which expands as you adopt higher and higher levels of confidence. And often that 99% confidence interval is so expansive as to be uninformative. You know, the standard deviations here are, in this example, and we'll find in other examples, are abnormally low. A standard deviation of 15 on this IQ mean suggests that these scores are relatively homogeneous. And if the scores are relatively homogeneous, then the standard deviation will be low, so that this error component or error estimate will also be low. But as the variability of the original scores increases, so that range, that interval, increases to a point, as I've said, where it may be quite meaningless. You may, at a 95% level of confidence, be able to say that, for example, the average GPA of some population is 2.62 plus or minus 0.3. But if you go to a 99% confidence level, it may now be 2.62 plus or minus 0.45. And I would suggest that a 0.9 plus or minus 0.5, a 0.9 range on what is theoretically only a 4-point scale may render your estimate not at all useful. I think they're just wheeling the heavy guns into place. We resisted the whatever that creature was that used the little tap hammers earlier in the semester. But now I think the heavy guns are coming into place, and I just hope we can stay on the air. You know. Good luck to you all. Are there any other questions? Somebody outside has a question. Let's look at then situation number 2. Situation number 2 is once again one in which you're estimating mu. That was the case in the first situation. Similarly, n is large. But in contrast to the first situation, sigma is unknown. In the first situation, the only difference between situation 1 and situation 2 is that in situation 1 sigma was known, and in situation 2 sigma was unknown. Let me simply work through an example of this, which is on page 164. Page 164. It says, the bottom paragraph, let us close this section and so on. Average income for a random sample of a particular community is $35,000. A random sample, that is X bar, equals $35,000. With a standard deviation of $200, that is, the standard deviation of the sample, S, is $200. And we find below that N, sample size, is 500. And it asks, what is the 95% interval estimate for the population mean mu? Yes.
Wouldn't we have to get the sigma first, or like compute it first, since you said like we couldn't do the estimate, like we would have to know the mean and the sigma and stuff?
Contraire, mon frère. You will find this. That's a reasonable question. But when you don't know sigma, which is common, I mean, this is the situation in which the researcher typically finds himself or herself. Yeah, they've sampled from some population, and they've computed the statistics, descriptive statistics associated with that sample. So they know on the one hand X bar, the measure of central tendency, and on the other S or S squared, the standard deviation or variance, the measure of dispersion. They don't know anything about the population. So this is a much more realistic situation. We determined last time that the formula for estimating mu was X bar plus and minus some z-score multiplied by sigma over the square root of n, where that z-score was a function of the confidence level. Yes? Let's just try applying this. That equals X bar. In this case, X bar is 35,000. Yes? Plus and minus. We were instructed to compute the 95% confidence level. Therefore, Z is equal to what? Plus and minus 1.96. It's here that we run into trouble. The standard deviation of the sampling distribution, which according to central limit theorem is sigma over the square root of n. If you don't know sigma, what might you use to estimate sigma? Yeah. Don't be afraid of this. Don't be afraid of this. Nobody's going to laugh if you get it wrong. I'm just... If you don't know this, when we didn't know... Well, let me go back to point estimation. All right. When we didn't know the population mean, what did we use to estimate it? The sample mean? Yes? If we don't know the population standard deviation, what could we use to estimate it? No. Let's get this logic. Really, hold on to it for a moment. If you don't know the population mean, and you use the sample mean as an unbiased estimate, what happens when you don't know the population standard deviation? Would you use the sample standard deviation, right? We would use S as an estimate of sigma. What's the problem in using S as an estimate of sigma? And this question isn't just directed at you.
I'm guessing on this, but not as accurate.
Not correct. Why can you use X? If the sample size is large, and if the sample is selected randomly, you dip in, pull out some...
Could like the central limit theorem apply to it or something like that? Like the farther it is away from the thingamajig? No. I don't know.
I don't think that central limit theorem references the thingamajig, but we can always go back and check.
The further it is away from the mean or something like that, the more inaccurate it becomes.
I'm looking for one word. It's not accuracy. What is the magic of random sampling? Is the magic that the sample mean will always equal the population mean? Is that the magic? I need to go back. Is there anybody else? I've got to see the back of your heads. Yep, they got backs to these heads. I thought they'd just put faces on these things. Faces on sticks.
Equal probability of selection?
No. Let me go a little further with this story. When you select a sample randomly, you and I observed at the time that it is extraordinarily unlikely that that sample will be a mirror image of the population. We sort of recognized that again when we were talking about point estimation. I said you reach into a population, you select out 200 persons at random, you administer a test of intelligence, you discover that the average score of that sample on that test is 105.0. I said, what is your best guess of the population mean? And eventually you said 105. That is, your best estimate of mu was X bar. Why is that the case? Here's the beginning of your answer. I've got an answer, Dr. Douglas. It's because when samples are large and they're selected randomly, the mean of the sample is an blank estimate of the population mean.
Representative?
Not representative.
Biased?
Not biased. How about putting it the other way? Unbiased. That's why your best guess of mu is x bar if the sample size is large and if the sample has been selected randomly. Because the sample mean under those conditions is an unbiased estimate of the population mean. You recognize this implicitly when you were computing mean scores. It doesn't matter whether it's a sample or a population. You compute the mean in the same way. You add all the scores together and you divide by the total number of scores. When we were talking about standard deviation and variance, what did we observe? Well, let me ask you this. Did it matter? Did you compute population standard deviation or variance in the same way that you computed sample standard deviation and variance? I'm having some fun, just going to sleep. When you computed sample, only you did this on the exam.
One is over n minus one is not.
I think.
On sample, you divide it by n minus 1. On population, you divide it by
And
n.
why do you do that?
Because you're accounting for the fact that it's an estimation or an unbiased representation.
No. No. It's not either or. The issue is that x bar is an unbiased estimate of mu. But S is not an unbiased estimate of sigma. S is a biased estimate of sigma. And to correct for that bias, you had to change the denominator in your computation from n, when you were computing variance and standard deviation of a population, to n minus 1 when you were dealing with a sample. If we're then going to use S to estimate sigma, you have to recognize that S is a biased estimate, not an unbiased estimate of sigma. And so you compensate for that bias in the very same way that you did when performing the computation. You use n minus 1 as the denominator and not n. So the only change from situation 1 to situation 2 is that sigma is known in situation 1 and unknown in situation 2. As a result, you have to use S rather than sigma in your formula. And when you do that, you have to recognize that S is a biased estimate, and you correct for that bias by using n minus 1 in the denominator. And that formula is formula 7.2. And it's on page 164. So in this example, our estimate of mu is 35,000 plus and minus 1.96 multiplied by S, which is 200, divided by the square root of n minus 1, and n minus 1 is 499. Would you agree? Yes. Yeah. And if you perform that computation, apparently, according to Healy, the answer is $35,000 plus and minus $17.55. That is, based upon this sample of 500 individuals with an average income of $35,000, you would now be 95% confident that the average income of the population was somewhere between $35,000 minus $17.55 and $35,000 plus $17.55. Let me make two observations, and then I'll answer any questions that you have. The first observation I have is that this is enormously powerful magic. It's enormously powerful magic. To be 95% confident or 99% confident that your estimate includes the population value based upon examination of 200 or 500 persons selected randomly from a population is an enormously powerful statement. You're expressing not only something about the estimate, where it is, its value, you're doing so with an extraordinarily high level of confidence. Jurors are admonished that they must be convinced beyond reasonable doubt. I do not know what inhabits the minds of jurors, but I know that beyond reasonable doubt statistically means at least 95% confident. And I'm willing to bet you that people are found guilty in courts of law when jurors are substantially less than 95% confident that they're guilty. So this is an enormously powerful magic. The second observation I have to make is in regard to this example in particular. This is a ridiculously low value. It's a ridiculously low interval or error. I mean, what we've said here is that we're 95% confident that the average income of this group as a whole, this community as a whole, is somewhere between $34,982.45 and $35,017.55. It's an absurdly narrow range. And it's an absurdly narrow range because this measure of standard deviation, this measure of dispersion, is ridiculously low. If you were to select a sample of what this says is that this sample of 500 incomes are very homogeneous. They're very similar to one another. In reality, the values that are behind, the individual scores that are behind this mean score would, in all probability, be much more disparate, so that the measure of dispersion, the measure of disparity, here standard deviation, would be much higher, so that this score would be much higher, that is, this score would be much higher. Are there any questions about interval estimation in regard to situation 1 or 2? Yes. You have to...
Using these numbers, based on these numbers, how much higher would the standard deviation have to be to make a difference in the plus or minus Like, would it be 500 or 300 or?
In this situation, standard deviation, if it moved at all, if it moved upwards at all, would increase this bottom line error. Obviously, if it moved minimally from 200 to 205, then the bottom line change would be minimal. But if it moved substantially from 200 to 500, then this bottom line value would be substantially higher. If it, again, if it were 1,000, it would be higher still. And the more discrepant those original scores, then the higher the standard deviation. It wouldn't be unrealistic to suppose, for example, that one might have a mean of $35,000 and a standard deviation of $8,000 or $10,000, which would $10,000 would increase the score by a magnitude of 50. And that comes back to the question of why not use just 99% confidence levels rather than 95%, because the trade-off, at some point those intervals can become so expansive as to be uninformative about the population value. That's not illustrated in the examples that we've looked at so far because of the unrealistically low measures of variance. Are there any other questions? What I would like you to do is read through this material. There is one more situation that we'll examine, and that is the situation where you're estimating P subscript U, which is the population proportion. And you're using P subscript S, the sample proportion, to do that. This is the interval estimation situation most familiar to all of you, because it's the political science, it's the voting thing. I hope that one thing you observed today was that while the situations change, and so while the formula changes, the logic remains the same. And the logic, not only the logic of the analysis, but the logic of the formula that you use remains the same. It's the point estimate plus and minus some number of standard deviations. Actually, it's the point estimate plus and minus either 1.96 or 2.58 standard deviations. Standard deviations of what? Standard deviations of the sampling distribution of sample means, which is, according to central limit theorem, sigma over the square root of n. When sigma is unavailable, you use S, the sample standard deviation, but correct for the bias in that estimate by using n minus 1 rather than n in the denominator. This second part of the course will be obscure to you. You will find it extraordinarily difficult if you are intimidated by the change from situation to situation. That's nothing more than a red herring. What remains stable, not only in interval estimation, but when you're comparing the two group means, for example, males versus females on the SAT, what remains stable is the logic. So my recommendation is that you focus on that and not on the really, to some extent, irrelevant issues that are changing around you. It's important to know what situation you're in, because that determines the formula that you use, the data that you need, and how you combine those data. But I don't want you to be intimidated by those changes, and I would therefore recommend that you focus on what is a stable logic. I will see you next time. Adieu.